So this is joint work for Yip, Jason, and Guido, and of course they did all the hard work in this presentation. So I mean, this talk starts off with a contradiction, right? All discrete optimization solving technologies work on integers. That's how they work. But yet we're going to say no discrete optimization model should include integers. So you'll see that I'm kind of cheating a bit in that definition, but that's what I'm going to try to convince you of today. Okay, so quickly, for most of the people here, this is not going to be difficult, so I'll go quickly. But modeling languages, right, are designed to express, at least in our case, discrete optimization problems, and then they translate them to a suitable form for solvers. And there's a small class of these kind of domain-specific languages, and we're going to be talking about MiniZinc today. And this is a solver-independent, high-level, and extensible modeling language, which is used widely around the world. Okay. And so MiniZinc supports various different kinds of solvers, constraint programming, sat modulo theories, MIP, and Boolean satisfiability, as well as local search solvers. And typically for them, the problem is that you can only give them a set of decision variables, perhaps of a restricted type, like they might just be bool if we're doing a satisfaction problem, and a conjunction of constraints, and often restricted to a particular type. If it was a MIP solver, they'd all have to be linear or more or less linear. Okay, and so the MiniZinc framework is really this thing where we take your model, which is a high-level language, we take your data, and then we put that through MiniZinc, and we create a flat zinc, which is the input to a solver, specialized for that particular solver. Then we run the solver, and we generate a solution, and then we report that back to you. And one of the key features of MiniZinc, because it's a constraint programming modeling language, is that we have global constraints, and these allow us to capture frequent combinatorial substructures. They're very useful in terms of modeling because they make it more concise and higher level. And there's lots and lots of different global constraints. They won't really be the focus of what's going on here, but I will talk about a few of them just to bring up some of the points. I'm going to talk about integers or lack of integers. All right, so here's a MiniZinc model. I hope most people in the room with me will already know what this does, but let's go through it quickly. So we've got datas, right? So here we've got an array from 1 to n, which maps each product to a weight. We've got decision variables. So here we've got an array of size 1 to k, which maps 1 to k to a product. Basically, we've got to choose in this problem, we're going to choose k products to take in our knapsack to maximize our profit. We have to fit within the weight limit. So we have a global constraint here because we have to choose different products. We're choosing k different products. So we have this constraint saying the things in this chosen array all have to be different. And then interestingly, here's a feature of MiniZinc or CP modeling where I look up, right? You see, I look up the weight of the product which is in chosen of I. So I'm actually looking up the weight of a variable decision. So that's not easy to write in other non-CP modeling languages. Okay, and this is a model that works. It will return some answers. Wonderful. We can write a simple knapsack problem in MiniZinc. Okay, so the problem with discrete optimization is basically once the model compiles, that's when the real problems begin. So we can have a few different kinds of things going wrong. So we could have too many solutions, right? So that means typically our constraints are weaker than they should be. This is not difficult to find usually because you have the wrong solution as a guide, and then you sort of say, oh, which of my constraints should have removed this solution? And so it sort of aims you directly into what part of your problem, what part of your model is going wrong. Too few solutions is much harder because now you're missing solutions, and the model may just say unsatisfiable, says there are no solutions. And then you need to do things like look for a minimal unsatisfiable subset, so some small set of the constraints which illustrate the same problem, and you have to carefully explore your model. But you can do even worse than that, is that you ask the question and the model never returns. It just runs forever and ever and ever and ever. And this could be for two reasons. Could be there's a bug in your model, or worse, a bug in the solver, but let's assume not. Or you're asking the problem that's just too hard to solve, that you're not going to get an answer within 100 days, right? So it wouldn't matter how long you were willing to wait, you'd get no answer. So you don't know if it's a bug or just the problem you're asking is too hard. And you don't have trace debugging, right? So solvers are usually black boxes, and trace debugging is not useful anyway, because if you look inside them, right? The search tree can have millions of nodes, so it's very hard to track what's going on inside a solver. And so the key takeaway from this is, if the compiler, if our MiniZinc compiler can recognize errors for you, that's extremely valuable, because it's going to make you avoid a whole lot of time trying to track down bugs, which are very hard to find. All right, and so MiniZinc has a relatively simple type system with Booleans, integers, and floats, sets of integers, or I won't talk about them much here, and then you've got arrays of the above and automatic coercion. So it's kind of reflecting what solvers can mainly do. Some solvers can directly handle sets of integers, many can't. So integers look to be ubiquitous, right? They're used to model sets of objects in our problems. They're also used to model things like position. If I'm packing, I'm determining a position to place an object. They're used to model time when I'm scheduling. I'm picking a start time. They're used to model order. If I just have ordering number, this is number 1 in the order, this is number 2 in the order. So the question is, how can we remove integers from our discrete optimization modeling language? All right, so let's start. So enumerated types are very, very useful for discrete optimization, because many times we're reasoning about a set of objects, right? So inside the solver, they'll be represented by integers, but in the model, we're much better off representing them as an explicit type of objects. And then we stop confusing them, right? So we can define the enumerated type color, which just has red, blue, and green in it, right? And now if we try to use, and we've got an enumerated type position, which is just saying, oh, we've got 3 positions. We don't care what their names are. And if we try to use a color in where we want a position, or we used a position where we want a color, we'd get a type error. Yeah. So these have advantages. They're better self-documentation of model, but you get now type safety. If you try to use a enumerated type in the wrong place, then the compiler will complain. And I was sort of saying, I hope I convinced you that it's very useful, the compiler, to complain. So let's get back to the model we were looking at before. So as I said, this model works and will return answers. Anyone see the bug in the model? Not easy, but there is a bug in the model. This model doesn't do what I think it should do.
Is it the fact that not, yeah, that you're saying profit I?
Yes, Kelvin is good. All right, why don't we, so here you can see we're using integers, right, to define products. Why don't we use an enumerated type, right? So all we did was replace products as it's a enumerated type. We're reading it from the data. Nothing else changed in our model. Now this model fails to compile, right? And exactly, it's because here, if you look at profit of I, we're taking I as in 1 to k, but profit is an array which maps products to integers, right? So before, when a product was just another integer, this was correct. Now this is a type error. So enumerated types have found that bug for us. So we didn't have to go and do a whole lot of work to track it down. So enumerated types in MiniZinc are ordered, and they support these kind of operations. You can do equality, not equality, less than or equal to, and you can take an enumerated object and find the next one in a list, and you can take mins and maxes. You can have sets of these objects. And in fact, you can explicitly coerce integers to enumerated types using this to_enum, and I'm just showing you this because I'm going to show you how we map these things down, because really this is kind of syntactic sugar. At one level in the MiniZinc compiler. After we've done our enumerated type checking, they're of course going to be replaced by integers, right? And if you think about how would I build enumerated next, right, which just takes an arbitrary x of some enumerated type t, then I basically take x plus 1, which sort of takes this enumerated type, and as soon as it's used in arithmetic, it becomes an integer, adds 1 to it, and then maps it back to the enumerated type. That's a simplified version for the purpose of the presentation. All right, so we've got rid of some enumerated types. Our objects, some integers, our objects are now integers, but suddenly, sometimes that's not enough, right? Sometimes when we use integers, but we'd like to use enumerated types. So here's a pizza ordering program. So you've got a set of vouchers that you can use, and they're like something like buy 1, get 1 free, right? Or buy 2, get 3 free, or whatever. And if we're making a decision about how we've got a set of pizzas we need to buy, we need to understand how we buy them. So here's one model using integers. So I'm saying, well, I can get this pizza in 3 different ways. I can get it for free if I'm getting it for free using voucher J, right? I can just buy it. So if how equals 0, I just buy it, right? I can always just buy the pizza. Or I can buy it in order to enable voucher J. So if I'm buying 2, get 3 free, I need to have 2 pizzas which have, +1, meaning they were bought for voucher 1, and then I can get 3 pizzas with -1, meaning we got them for free voucher 1. Yeah. So I'm using these integers to represent these different cases. And then the kind of main constraint is, the ones you buy have to be more expensive than the ones you get for free. All right. But here's an alternate. Now, the problem with what we saw so far is, yes, we can definitely have an enumerated type for pizzas, but we can't really have an enumerated type for vouchers, right? Because we got 2 copies of vouchers in our enumerated type. We're using the voucher to get something for free, and we're using it to buy something. So here, this is an extended enumerated type. So here we're saying we're replacing this -m to m by just these enumerated type values. So I can say, oh, if the use is f of voucher, then I got this for free using this voucher. If it's none, I just bought it. And if it's b of voucher, then I bought this pizza, so I paid for it, but I used it to make me able to use this voucher, right? And then interestingly, I can write my constraint slightly differently, because I take how did I buy this pizza? So this b to the -1 is the inverse. It'll strip off the b if that's the case. It'll fail otherwise, right? And then I put a free in the front. So this is a way of converting a b of voucher to an f of voucher for the same voucher. So this is checking, did I buy pizza 2? Did I get pizza 2 for free by using the voucher which I used to buy pizza 1? And those are the ones where I have to make sure the constraint holds. All right, so we've got an enumerated type for vouchers, and now we've got this extended enumerated type because I'm using voucher in 2 different ways in my how. Yeah, and then I'm using these constructors f, right, and b to the -1, which is the inverse constructor, to manipulate these objects, these use objects, in order to check constraints. So if you look at this type extension we saw on the previous example, it's basically building an enumerated type which has like 2 times the number of vouchers plus 1 elements in it. And you add this construction functions, right? So f takes a voucher and returns a use. B takes a voucher and returns a use. But we also have these deconstruction functions. So f to the -1 takes a use, and if it's a form f of voucher, it will return the voucher. If it's not, it'll fail. It'll become undefined. And similarly for b to -1. And so this has made our program type safe, more concise, and more self-documented. All right, so interestingly, under the hood, we can map this all just down to MiniZinc, right? So we create a new use, which has just got 2 times the number of vouchers plus 1 elements in it. And then we can build up these functions f, b, f to the -1, and b to the -1, just using existing MiniZinc. So that's hidden behind the scenes. The main important part of the type extension is the type checking before we do this rewrite. All right, now once we have this, then we start to we can generate quite complex code. So this is part of a little VRP problem. And if we look at the key data structure, it's here. So in VRP, I'm going to build a graph over these nodes. So I have a node for each customer, I have a start node for each truck, and an end node for each truck. So you can see that's an enumerated type, an extended enumerated type. And then the main decisions are, for each node, I need to know when do I arrive there, and for each node, I need to know where do I go next, which next node do I go to. And then the important constraint in this thing is I look over all my nodes which aren't end nodes, right? Any node which is not an end node. Now I can work out how long, okay, when can I arrive at the next node from this node? Well, I took my arrival time at my current node, and then I have to work out the travel time So the travel time is from the location of this node, right? If this is a customer node, then I can look up its location in this customer array, right? So I strip off the C to get just a customer, and then I look up its location. And if it's not a customer, then all the locations are just the depot, because all the trucks start and end at the depot. And similarly, I do the same for next event. If the next event is a customer node, then I look it up using this cust to the -1 of next event to find the actual customer, otherwise the depot, right? So I can build this complicated pieces of code, which is correct, perfectly good, it's type safe, etc. Will always work, but it ends up being quite lengthy, wordy. So we introduce expression x default y, right? So this says this evaluates to x if it's defined, and otherwise you get y. So it's kind of like an if then else for undefinedness. Now, if I do that, I can just replace what I had before by this expression. Whoop, there we go. So if you look at my travel time, I try to look up the customer -1 of this node. Now, if this node is a customer node, this will succeed and I'll get its location. If it's not a customer node, this will give me undefined, and then the whole thing will be undefined, in which case I'll get depot. So I can build this little if then else essentially using this default notation to get a much smaller version of the same constraint. And there's some benefits of this as well, because we can actually, if we see this kind of expression, which is common, an array looking up at f of I default y, we can actually build an array which will do this directly. So here we see, we want to map nodes to locations, right? So here it's really like a copy of the code we did here, but we make it an array. So if the node is a customer node, we look up its location, otherwise we get the depot. We've seen that code before. We put that in an array, and then I can just map a node, right, to a location directly. I can just use that twice, and this can automatically be done from the default expressions on the previous page. And this generates actually very efficient code for the solving. All right, let's keep going. What else can we do? All right, so here's a slightly different version of our problem, right? So, okay, you can see I got rid of my problem. I was using I instead of chosen of I fixed that. So this model again runs and returns answers. So no type errors on this version of the problem. Can anyone see the difficulty with this problem?
Maximize profit.
Maximize profit. Yeah, okay, look what we're doing. We're summing up the weight. So we're maximizing weight, but there's another more clear thing. So that's definitely, we're not doing the same thing as we said. We've switched weight and profit, right? So here, if you look at this, we're summing up the profit and comparing that with the weight, right? So profit is about worth and weight, limit is about weight. So we're mixing up two kinds of things that we're comparing. You shouldn't be summing up profits and then comparing it to weight. It doesn't make any sense.
Okay. So
yeah.
No, you're about to go to it.
Yeah. Okay, so unit types. So we have an extension of MiniZinc where we can now talk about the type of an integer, right? The unit of an integer. So here we're saying, okay, limit is a count of the number of kilograms, right? And the weights are in kilograms, but the profit is in cents. Yeah, so you can see that our integers have this unit attached to them now. So if we take this model where all I did was add these units, suddenly now the compiler goes, hang on, there's a type error here, right? Because this thing sums up profits, which are in cents, and it compares it to limit, which is in kilograms. Yeah, so I've now can detect the error and I know there's something wrong. Yeah, so this linear equation involves two incompatible units, kilograms and cents. All right, so in MiniZinc you can define, so there's two notions for units. There's both a dimension, right, which is the type of the unit, and then units themselves. So we have unit type weight, so that's a weight units, and then unit type worth. And then you can imagine for weights, there are many different units we can have. We can have grams, and then kilograms is just 1,000 grams, ton is 1,000 kilograms, and maybe a US ton is 907.185 kilograms, right? And similarly, you can have cents, which is a unit of worth, and we have dollars, 100 cents. We can even use Unicode symbols. I guess that was, we want to use cents as a thing. That's allowable in MiniZinc, although it's harder to type. All right, once we have our basic unit types, we can also derive unit types from them. So let's talk about unit type distance. So that's another dimension. We can have meters and kilometers, and then we can talk about area, which is just, this is a derived unit dimension, derived dimension, which is distance times distance, right? And square meters is a derived unit of type area, which is meters times meters. And then we can have time as another dimension. We can have seconds, minutes, hours. Then we can have velocity, which is a derived dimension, which is distance divided by time. And then we can have a dimension, a unit for that, like kilometers per hour, right? Which is exactly kilometers per hour. Okay, so we can build up these derived dimensions, and we can build up derived units as well. Okay, interestingly, often in discrete optimization modeling, we don't, so a lot of units are used in complex physics stuff, where there's a lot of grams and kilograms and meters per second and tons and energy and making sure those all agree. That's not often what's happening in discrete optimization models. So often we have just one unit type for, let's say, the particular dimension that we care about. Like in our example there, we're only using kilograms to talk about weight. We didn't do any complicated conversion from one weight to another. So we allow this notion of abstract units. So here we're saying, I'm introducing this abstract dimension called the limit dimension, right? And then I've got a unit LU, which is limit dimension unit, right? A base unit. And I've got a VU, which is some worth unit. I'm not telling you what it is in dollars or cents. It's just some worth unit. Since I only deal with one version, one unit for each dimension, then I can just, instead of using cents and kilograms, I'm just using this, limit unit and the value unit throughout my model. Nothing else changes. And then, of course, the thing is, because I'm writing cents, but I really want to talk about millions of dollars, of course, nothing changes in the model, but it becomes less useful, less realistic. So that's an abstract limit dimension, the abstract limit unit, and then our abstract worth unit, and then we use them throughout our declaration. And of course, we give the data without units. It's interesting, we would like to be able to give the data with units, but typical ways of handing over data aren't easy to add units to. We could do it for our DZN file. We've chosen not to at present. And another thing, this is interesting, that this came from a reviewer, so it's very nice that a reviewer could improve your work for you. So in the previous slide, we introduced this limit dimension, and then we introduced an abstract unit of the limit dimension. But often in our models, we only have one unit of each dimension. And so basically we're allowed to use, right, the dimension itself as a unit. Right, it's a default. If that's the only unit for that dimension, you can use it throughout your model. Just saying, okay, we're just talking about limit dimension, whatever it is, it doesn't matter. So we use it as a unit in various places, and yeah, nicely, that was a suggestion of one of the reviewers. It was very easy, of course, to modify our system to support it, and I think it's actually it's very useful, because if we look at discrete optimization models, almost always you have either one or two units of the same dimension. So typically in scheduling, you may have more than one unit. You might be doing some things on the 1 minute and other things on the half day. And so you've got two different units. All right, let's look at coordinate types. So, remember to stop me and ask questions if I'm rushing forward. So units can expose lots of errors, but you can still hide errors in your model. So here's disjunctive, right? So disjunctive takes an array of start times, an array of durations, and makes sure that those tasks that are represented by that don't overlap. And this is a correct definition of it, right? We're taking the start time is in time units and the duration is in time units. But then I can write this constraint at the bottom here, okay? Disjunctive duration start, right? So it's an error because I put the durations where I meant to put the start times, I put the start times when I'm meant to put the durations. But there's no unit error because they both have the same units. So no error, right? But there is really a difference between start times and durations, okay? They are actually a different kind of thing, right? So you've got this notion of, we call them coordinate unit types. So a coordinate unit type is a measurement with respect to some origin. So when we talk about time, right, if I talk about time 0, that's the first time that I'm considering in my scheduling problem. And time 20 is the 20th time, right? And that's different than a duration. A duration of 20 doesn't tell you when this starts. It's not a coordinate, it's just a difference, in fact, between coordinates, right? So your start times are coordinates of S, some coordinates of seconds, let's say, and your durations are non-coordinates, or we call them deltas, but basically normal unit types are these difference types, right? They're talking about the difference between two coordinates, all right? And as soon as we introduce coordinate types, we can restrict what we can do, right, in addition and subtraction. So you can take a coordinate type and add a delta type, and you get a coordinate type back, right? You can take two delta types, so this is normal, and add them together, you get a delta type back. What you can't do is take two coordinates and add them together, right? It doesn't make any sense to say, okay, we're taking 17 degrees Celsius and we're adding 19 degrees Celsius, right? Because Celsius is an absolute notion, right?
Do you have to define certain types as coordinate?
So we allow any base type to have a coordinate version, right? Because we couldn't see, like, there's not a real notion of an origin for velocity, right? So you can have an origin for position, but you really can't have an origin for velocity. Velocity is already a delta notion, right? It's a change in position.
Yeah.
So only base types. So you can automatically, we have this coordinate notation, which says, okay, I can have a coordinate of meters, a coordinate of seconds, a coordinate of any sort of unit, of any base unit, right? But not a derived unit.
Okay.
Yeah. Oh, the other thing with coordinates you can do coordinate minus coordinate, because you're a delta. Obviously, that's kind of the definition of a delta. And you can subtract a delta from a coordinate to get another coordinate. But you can't take a delta and subtract a coordinate. That's an error, right? Doesn't make any sense. So this means you find more bugs. All right, so here's our example. So this example doesn't have a bug in it, but if you look at, say, this, right? So start of JM is a coordinate of the time unit, and duration is a delta of the time unit, and then we add those together and we compare them to a coordinate of the time unit. So that is type correct. And similarly, here we're calling it with a start array, which is a coordinate, is an array of coordinates of time units, and a duration array, which is an array of time units. So it's also type correct, right? But we can't add start times together anymore. All right, let's keep going. In nums and units. So this is interesting. So if we look at our model now, there's one integer still left, right? So everything else is a enumerated type, or it's got a unit type attached to it. What is K? What kind of unit is K? What kind of integer is K?
It's natural.
Natural, sure, but so 1 to K, but does it mean something more than that? How are we using it in this model? Is it just a number from 1 to K?
I guess it's just as an endpoint for the product.
Indexing.
As indexes.
But actually there is a real type here. It's a counter of products.
Okay.
Okay, right? Because an array of K products is actually a counter of products. So each enumerated type also introduces its own unit type, yeah, for counting that thing. So you can think about someone speaking behind. Ryan should shut up.
Sorry for that.
Okay, so if you think about it, if I have a set of type T, right, this enumerated type T, then what the cardinality does is return a count of type T. Yeah. And interestingly, discrete optimization problems frequently involve counting. And this is interesting, for, at least for me, because this is a unit type you don't see in any other unit type systems at all, right? But in discrete optimization, we do a lot of counting, right? So this counting stuff we want to separate. Counting products is not the same as counting, I don't know, classes or counting some other pizzas or whatever, right? They're not the same. Okay, so now we can finally get rid of the last thing. So we say this is an int at product. Now remember, that's different than a product itself, right? So this chooses a product. This says this is an integer counter of products. Yeah. So this is the number of products that we choose. And then we're going to build this range type which says 1 as a counter of products to k, right? And then this array now, right, from 1 to k is really not just an arbitrary integer, it's one of these product counter integers. Yeah.
Is duration a counter of time?
Is duration a counter of time? Well, yes, but
Not use the.
we're only adding counters to enumerated times, right? Because duration is a delta of time, and we already have that notion, right? So we don't need to do anything extra there. But we definitely see this kind of stuff happening in our models where we have counters of enumerated types, and we should use those counters. Right, so there's a range over the unit types. Okay, but that's not quite enough. We can have more complicated cases. So here, what about if we have an enumerated type which is different resources? And we don't want to really mix up counts of those resources. So here's a little production planning problem, right? So we've got some products, and for every product we've got a profit, and we've got some resources, and for every resource we've got a capacity, and for every product and every resource we have how much it consumes to build one of that product. And then we have to decide how much to produce of each product, right? So we have this constraint here, of course, which says for every resource, if you sum over all the products that you bought times the amount you produced, it better be less than equal to the capacity that you have of that resource. So how do we make this unit type safe? Okay, so you can see we're introducing unit variables here. So here, I'm saying array P in product. So this array, I'm giving a name for the index that I'm looking at. I'm saying the product, the type of every profit entry in this array, each entry is different, has $ per product P, the specific product P, not arbitrary product P, but the specific product P, which we're talking about in that location, right? Because this maps products to profits.
Is it like sort of meters per second or?
Well, yes, it is, but except that this is rather than the seconds, which would be the same for everything in the array, this is P, which is different for every product in the array.
Okay.
Right? And then you can see our resources. Okay, this is int, which is returning a capacity in the particular resource type.
Oh, right.
So we're using the elements of the enumerated type as units.
Yep.
Yep. And then the interesting one is, okay, what does this consumption say? It's basically saying how many resources per product you need, right? And then if you look at this thing, right, we've got a different unit per element. We've got an iterator in our definitions. That's how we get hold of this P value, like this variable, which tells you which particular product you're talking about. And then, okay, we're counting, right? We're choosing a counter per product type, right? So each of these decisions has a different unit. And then finally, if we look at the unit types, at the important constraint, right? This thing has type resource divided by product, right? Resources per product. This is type product, and this is compared with a particular resource. So it's different for each iteration around the loop, but it adds up to be correct, right? Because this, we add up lots of things of R of P times P, which is just R, and then we compare them with R. So we have quite dense type safety. To break this type safety, it's where you mix up two resources, like where you start we're using one resource where you're meant to use another one. And you can get it out of copy paste errors, but it's not that frequent.
So in a sense, every enumerated, like every element of an enumerated type is its own type.
It can also be its own unit, yes.
Okay.
Yeah. Okay, so interestingly, for that example, the type checking is easy enough, and indeed, with the cases where we see this used, it's fairly easy. We have the syntax. So the only way of writing this is in this rather limited way, where you're using an index into the array as this unit, right? So it feels like it's worth it to us because it does limit some type problems. Although it becomes more burdensome, right? Because obviously the more we have to write above our untyped program, the more value we need to get out of our type checking. All right, keep on going. Oh, we're going okay. So another thing that we use integers for in discrete optimization problems is ranking or ordering things. So here's the historical stable marriage problem. Interestingly, I can't change it to a more modern stable marriage problem where you can have any gender match with any gender, because then it gets rid of the problem that I'm trying to show you. Okay, so here, this is a classic thing. We've got n men and n women, and each woman ranks each man, and each man ranks each woman. And then we have to choose for each man who their wife is, and for each woman who the husband is. And in a stable marriage situation, everyone prefers, for every alternate, let's say if I'm a man, then every woman that is not my wife, either I prefer my wife to them, or my wife prefers me to their partner. So there's no reason for two partners to swap.
They prefer their husband over you.
Oh, sorry, yes, okay, you're right. Every woman, I prefer my wife to them, or that woman prefers their husband to me. Yes, absolutely. Yes, correct. All right, and that's written here in glorious detail. Now, we're also going to, because enumerated type is ordered, we can use that as a ranking, right? So here we're going to introduce a new unit type, rank men and rank women. And then we're going to say, well, these are just, this is the woman's ranking of men. So these are ranking of men, and the men have a ranking of woman. And now, right, so we've got a new dimension we're just adding for ranking, and we use it as an abstract unit. And then basically, well, there's no error in this model, but if I had a rank men here and I compared it with a rank woman, then I would actually have a type error, right? Because one of them is ranking men and the other one's ranking woman. They're not the same unit, so that's wrong. So this allows us to avoid comparing male ranks and female ranks. And yeah, this problem goes away, of course, if we're all just talking about person ranks. So that's why I couldn't go to a more modern version of stable marriage problem. We can go further, right? We can associate each man or woman with their own ranking, just like we did for the resource types, right? So here you can see we've got a enumerated type of women. We're using each of those as a different ranking type, ranking woman and ranking men. And that will mean, right, that we couldn't compare the rank of one man with the rank of another man. Right, so if this was not M, as if it was another man, let's say M prime, then this would be type incorrect, right? Because we're comparing two men ranks and they're not the same unit anymore. So just like we did with the resources. All right, so on a kind of aside, we've actually had records in MiniZinc for a while now, and this is useful, right? So a record has this advantage. So here's a record which has a weight part, which is in kilograms, a profit, which is in cents, and a class, right, of every product, let's say, for our problem, if we added classes in. And then, so this has some advantages. We can package all the information about some data in one place, just in the record, right? But the bigger advantage it has in terms of type safe is now we have type safe table constraints, right? So the table global constraint basically says, so you have this argument X, right? You think of it as a list of variables, and you have an array of integers of size X. And basically the table says these X values must take one of the rows in the array, right? So this allows you to write an arbitrary relation. It's very powerful modeling capability. It's used a lot in different kinds of models.
Wait, so here the $sign E.
That just means enumerated type or integer. So basically you can see that this, you know, the number of I don't know if I've done it right. Oh yeah, rows is this dimension. Yeah, that's correct. So these are the columns dimension. So this is the rows and the columns, right? So the first is a single array which has to equal one of the rows in the other thing.
Gotcha.
Yep. So the problem with this is, if you look at this definition, all the columns are integers.
Yeah.
Regardless of whether they're representing a class or a weight or a thing. But once I have records, I can write the same constraint like this. I just say, okay, there's a tuple, WPC, the triple, is in the data, right? So there's some element in the data, which is this tuple or record, right? And this only works if W is of type kilogram, P is of type cent, and class is of type C, right? It'll not be type safe unless we do that. And this is interesting because, so I was recently in Sweden and Ericsson there, they gave a presentation where they claimed to have the world's largest CP model. It's used for configuration, live real world problem, written in MiniZinc. And it has lots and lots of ad hoc table constraints. Configuration problems are full of that kind of data of the different ways, different configurations, or parts of configurations. Basically, as soon as we added records to MiniZinc, they moved to use records everywhere instead of table constraints, just because of the type safety, right? So when you're building real world large problems, type safety matters. There's kind of direct evidence from one of our super users of MiniZinc. Okay, so the conclusion, we can remove all integers from a discrete optimization model in the sense that there should be no integer which doesn't have at least some unit attached to it, right? So it's not a plain integer, yeah? So objects, okay, we're represented by enumerated types. Parametric data, we can give appropriate unit types, even if it depends on units that we read in. And this improves type safety and possibly comprehension of models. That's the short location, of course. What about this guy? Still got one int left in my model. And in some sense, this is, you can see, this is just a counter of how many in my abstract problem. So there are some combinatorial problems where they're just integers, but very not sort of real life discrete optimization models don't talk about these, but there are some combinatorial problems where you're just dealing with integers, and so you have to live with it. But the main thing is, for realistic problems, you can basically should always have some extra information on integer in order to have the compiler find more errors for you. So we've had enums in MiniZinc for a long time. We added extended enumerations. If you look through the MiniZinc challenge models, then basically we can use extended enumeration types to improve models quite a lot. And enumerator types are used a great deal and probably could be used more in the 125 models we looked across. And these default expressions can be very powerful. It allows the compiler kind of automatically create these expert models by building these extended arrays for you. And you can get typically about 25% improvement in solving efficiency by using the default expressions. And then units, so we have an experimental implementation, which is a front end to MiniZinc 3.0. So once MiniZinc 3.0 will be out, you'll have units, it's all done. And the simple units seem very, very valuable and not difficult at all to support. The non-linears are fairly rare in discrete optimization. You didn't see a lot of, powerful, I don't know, meters divided by second to the squared or whatever, things that happen in physics. But discrete optimization models abuse integers all over the place, right? So units actually seem more valuable to us than in any other normal language. You'll find that there are unit extensions for almost every programming language out there, and they're almost never used, although they clearly should be, because I don't know if you know, the Mars Explorer, some $125 million piece of equipment, crashed into the surface of Mars because the US sent an instruction in the wrong units. Right, so it's an example of a very expensive unit type error. But so we think units are very valuable for discrete optimization and MiniZinc in particular. That's it.